Okay, hi again guys. So now let's continue on part 5 to discuss on the non-ideal flow models, which is we are going to use the segregation model. Okay, so from previous subtopic, okay, we have discussed on how to use the RTD in order to discuss on the non-ideal performance of your reactors. Okay, so to know whether your reactors having problems such as dead zone or bypass, short circuit, or let's say have a cyclic flow in the reactor. So for this topic, okay, for this subtopic, we are going to discuss on what are the function of RTD in to apply in diagnosing the reactor. So we're going to use the RTD to know the conversion or exit conversion of your reactors. Right. So the objective of this subtopic will be to predict conversions from the RTD data using the segregation model. So this is the model that we are going to use. And then we can predict the effluent concentration for the multiple reaction using the segregation models, right? So model to calculate the exit concentration and conversion, right? So we have this condition where RTD alone are not sufficient to determine the reactor performance. So we need something else to combine with the RTD in order to determine the reactor performance. Okay, so in this topic, I'm going to introduce to you. There are two models that we're going to use in order to determine the reactor performance. Okay, so which is the first one, maximum mixedness, and the second one is complete segregation. So what is maximum mixedness? So it is actually molecules are free to move anywhere like a microfluid. Okay, if you look into this diagram. Okay, so this is the extreme case of early mixing. Okay, so compared to this model, okay, which is complete segregation model, the molecules of a given age do not mix with other globules. Okay, so if you look at it, there are lots of globules. Okay, so molecules are kept grouped together in aggregates or packets. So different globule will enter and leave the reactor at a different time. So this is what we call it complete segregation model. So we are going to discuss about this in the further slide. Okay. Okay, if you look at this figure, okay, the globules behave like a batch reactor operated at different time. So you can see there is no material interchange between the fluid particles in the reactor. So like no micro mixing between the fluid particles. See the globules here. So similar goes in here in the PFR where you see at different point will give you a different conversion, right? So in order for you to know what is the final conversion, okay, so we use this mean conversion X bar. So what is mean conversion? It is actually XT/ET. So XT, it depends on what kind of reactor you're dealing with. If it's segregation model, you're dealing with a batch reactor. So you will include the XT that you will derive from a batch reactor design. And then you multiply with the ET that you get from your RTD data, or in case it is an ideal reactor, so you just include the formula that we have learned in the previous subtopic, right? So if you plot a graph, okay, so you will have XT/ET versus T. So the area under the curve is actually your S bar. So similar goes, that's why this equation means, so you need to find this area. So in order for you to solve this thing, so you need to use a numerical method like what we have learned in the previous subtopic. Okay, right. So the mean conversion is the average conversion of the various globules in the exit stream. So that's why this is X bar is actually when you have a different point in this reactor, you will have a different conversion. So we are going to find one mean conversion. That's why we end up using this. This is what segregation models are for, right? And then how are we going to solve this kind of situation? Okay, so first we need to determine xt from a batch reactor design equation. Okay, because we assume that it is a segregation model and it exists in a form of a batch process, right? So that's why in a batch reactor design equation, okay, so this is what, okay, this formula is very familiar to you, isn't it? Okay, so this is what you have learned in with Prof. Jim before, right? So for a first order equation, so your negative RA will become K CA, right? So your CA would be what? CA is actually CA not 1 minus X, right? Okay, so that's why in the end it will become this part, right? When you already insert all these two equations in here. So when you and then you also have to know that CA naught is actually NA naught over V. So when you have this is as a bring here, so this will be over V. So the CA naught will be cancelled out, and in the end you will end up to with this equation. So when you integrate this thing, it will be coming that equation through integration. Okay, so this is xt for first order reaction. Alright, so to compute the reaction with the first order reaction and complete segregation, insert the ET tracer experiment at xt from batch reactor design. So initially we know that x bar is actually the integration of xa et dt. So you will integrate. Okay, so let's go to the next type of reactor. So let's say you are dealing with ideal PFR and CSTR. Previously, okay, if you look into what my video last time, the ideal PFR, you will find that there is a formula for ET, okay, in PFR, and also ET for CSTR, right? So for the mean conversion, the formula is still the same. It's x bar is equals to 0 infinity xt et, right? So you will determine xt first. So how to determine xt? So it is first order. Okay, here is a first order reaction in a batch reactor. So this would be your first order. Okay, that is for batch reactor. But here, so for the segregation model, we will follow this, but instead of T, you're going to use your tau. Okay, so you will insert your formula in here, this part. Yeah. Okay, so you will see this one. And then this part is actually your ET for your ideal PFR. So in the end, you will find that your x bar for PFR would be this formula. So exponential minus to the power of k tau, right? So the same method applies for CSTR. In order to solve segregation model for CSTR, okay, the same formula, general formula applies, and then you insert the ET, okay, so insert the same ET, insert the XT, and the ET you find from the ideal CSTR, which is this one. Okay, if you remember, you may refer back to the previous lecture note, or you may refer back to your textbook. So this is actually your XT. So when you simplify that back again, it will be coming x bar is equals to k tau 1 over k tau. So this is for CSTR. Okay, segregation model, right? So this is example involving data. Okay, so this is non-elementary. I hope that you know what is non-elementary. Okay, so non-elementary meaning that your reaction order is not the same as the equation, right? So if elementary, you will have your reaction rate as negative RA equals to KCA. CB. This is elementary, but it is non-elementary. So that's why the reaction rate is this thing. Okay, will be carried out isothermally at 320 K in this reactor. It doesn't mention about what kind of reactor, but here calculate the conversion for an ideal PFR. And number 2 for the complete segregation model. So let's have a look on how to solve it. So given to you CA0, CB0, and also your reaction rate constant. So this is the set of data. So if you look here, there are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this is where your H is equal to 1. But starting from 10 to 14, your H is equals to 2. So you need to separate these two using two different Simpson's method. Okay. Okay, so now how are we going to solve this question? Okay, first we need to derive the xt. Okay, you need to derive your xt, right? Your xt. So this is the design equation for your PFR. So I believe that you have learned in Prof. Zain's class. So this is actually your negative RA. Okay, so it's given negative RA is equals to KCACB squared. So you just insert in here, right? And then FA0 is equals to CA0 B0. Okay, this is your fundamental knowledge. Similar goes by this one. This is your stoichiometry, right? So you insert all this equation back into the design equation, and then you cancel out. In the end, you will get something like this. Okay, the XA over 1 minus XA to the power of 3. So you integrate. Okay, I hope that you will do that the derivation back again, okay, by yourself, okay, so that you will understand more. Okay, so you solve the integration. You know how to solve the integration. There are appendix in your book that should stated how to solve this kind of equation. Maybe those who are good at mathematics, you can solve this one easy, right? And then you will find out that it will be in the end, okay, you rearrange, okay, it will be this equation. Okay, so bear in mind V over V0, this is a volume. V0 is actually your volumetric flow rate, so it's actually equals to Q over V0. So this is actually your tau. So that's why the equation becoming like that. Okay, so right, so when you rearrange back, your XA will be an equation like this. Okay, so then, right, so you if you aware just now, okay, so this ET is actually what you have calculated earlier. So in this case, you calculate first the ET. So remember, ET is actually what from your previous for my previous video, ET is actually what? T times ET, sorry, CT over CT from 0 to infinity. Okay, so you calculate back the ET here for this value here, right? So the next slide is having TET. Why do we need TET, right? So that we can calculate your TM, because tau is actually your TM, right? And then when you solve the TET, you solve for TM. Okay, and then in the end, you put back into this equation, then you solve for your PFR. So the question asks for PFR model. Okay, so this question asks for an ideal PFR. That's the way. So for